In this video, I wanted to talk about probability, specifically about the differences between experimental and theoretical probabilities and the fundamentals for using event spaces and sample spaces to help us determine theoretical probabilities. So our book defines the experimental probability of an event to be an estimate based on the likelihood that the event will happen, often based on an observation. So say, for example, you want to determine what's the probability that you would get, that your dice would add up to at least 8 if you're rolling 2 dice, like in the previous example we were talking about in the last video. Well, what you could do is you could grab 2 dice and just roll 10, 20, 30 times and sort of see, well, how many times would you get outcomes that add up to at least 8, and how many times did you not, and use that as a basis for that ratio. And the basis of a probability is a ratio between events, what are acceptable outcomes, divided by how many total outcomes. So let's say you were to throw those dice 10, 20 times. Let's say that you got, 9 pairs that add up to at least 8 and 11 that did not. We would say that it would be 9 out of 20 probability that we would get an acceptable outcome, and it would be 11 out of 20 that we did not. And we could convert that to a percentage or reduced fraction, depending on how we want to, describe a probability. Either is fine. Now, again, that would be called an experimental probability. That wouldn't necessarily be a perfect, correct, whatever you want to call it, answer, because that could change depending on who's running the experiment. That experiment could happen a lot of different ways. And if you're actually running an experiment, it's not going to happen the same way every time, most likely. So basically another idea is the more and more you would run that experiment, it would get closer and closer to what we call the theoretical probability of that event, or just in general, we would say what's the regular probability that an outcome would occur. Now, we don't know the regular probability by just rolling and just by doing an experiment, because we were not really sure. But if you did that 1,000 times, it would get closer and closer to the correct outcome. But we can always do it mathematically by using our definition. So let's just go ahead and take a look at that and then calculate a probability based on our previous example. So it says, for an experiment with non-empty finite sample space S with equally likely outcomes, the probability of an event A is given by P parenthesis A, end parenthesis, where this is sometimes what we call probability notation. P is the probability of this outcome or event occurring. Sort of like N standing for the cardinality, or the size of the set. P represents the probability of occurrence. Where it says that is equal to the number of elements of A divided by the number of elements of S, or N parenthesis A, meaning the number of elements in A divided by the number of elements in S. Or, a simpler way of saying this is, how many ways could this go right, and how many total ways could this happen? You can often think about the size of the sample space being the combination of the ways it could go right and the ways it could go wrong as the number that's in your denominator. But let's go ahead and put this into action. Let's look at number 3. It says, what is the probability that when rolling 2 6-sided dice, the sum of the rolls is at least 8? And so let's just say, we already have this event written out from the last video. E sub 2 was our event consisting of rolls that add up to at least 8. And so basically we want to know, well, what's the probability that would happen given my sample space? And the principle here that, what it says is that that's always equal to the number of objects in the event divided by the number of elements in the sample space. AKA, how many ways could this go right? So if we count up the cardinality of, and again, I'll use the S sub 2 notation to say, well, this is our event space from the second example, which consists of all combinations of the dice which add up to 8 or more, divided by the complete sample space. Now, we didn't actually write out the complete sample space, but we visualized it over here. We started to say, okay, well, we know there's going to be 36 elements in there, but we didn't actually count how many elements are in our event space, which would be, well, 1, There was 1 that started with 2, 2 that started with 3, 3 that started with 4, and so on. So 1 plus 2 plus 3 plus 4 plus 5. Or that's just going to make 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So basically we have 15 acceptable outcomes. And this is a much simpler way to express this formula. How many ways could this go correctly based on my parameters? And then it's always divided by, well, how many total outcomes would there be? And that was 36, right? Because we had 6 times 6 potential ways to those 2 dice could come out. And, you know, that this would be our theoretical probability, or again, just probability in general. If we were to throw 2 dice 1,000 times, the ratio of number of successes to number of total attempts would get closer and closer to this value. Which again, we could reduce this fraction since both those numbers are divisible by 3 by the rule for divisibility of 3, which if you remember was, you know, out of the digits 6, 9. Both of those are divisible by 3, so this is reducible by 3, but that would be 5 over 12. And that would be our simplest form of our probability ratio. We could even write it as 5 to 12, less commonly done, or as a percentage, which is what I usually like to do for my probability. So if you remember, you know, your fractions and dividing by 12, anytime the denominator is not a combination of 2s and 5s, that means we're going to have a repeating decimal here. And it's very, very common in probability to have outcomes which are not, you know, which are not whole. So in this case, 5 divided by 12 is our probability here, or 41.6% repeating. So you could write as a decimal, but which is totally fine. But I usually prefer percentage. Again, you could write it in any form. There's no correct form, but they're all, you know, equivalent. Or I could just leave it as 0.416 repeating. But one thing that you want to be careful not to do, or rounding is perfectly fine, but when you do round, you want to make sure that you're indicating that you're rounding. So notice how I'm writing it. I'm writing it exactly without any rounding to this infinitely repeating decimal. But, you know, I could always write it as, well, that's approximately 41.7% or whatever. Whoops, I do not. Yeah, there we go. To summarize this video and wrap it up, this is how we find probabilities in general. Now, you might ask yourself, do I need to do this every time? Do we need to write every potential option and every potential acceptable option? You know, do I need a full sample space and the full event space? Sometimes you don't necessarily need to list them all, but it's important that you think about every way something can happen, and really being thorough is the key towards being successful at probability, and really thinking about everything. And that's where tree diagrams can come greatly in handy.